Hello. Today we're going to talk about Chapter 5, the standard deviation as a ruler and the normal model. Okay, so first we need to understand what a z-score is. Okay, what we're trying to do is we're standardizing everything. So the idea is that we're comparing everything to each other. Okay, we're comparing them all to an average. Okay, so the z-score is we take our value, we subtract the mean, and we divide it by that standard deviation. Okay. The best way I can do is explain this through doing. Okay. Z-scores are think of it like your distance from the mean. Okay. It doesn't have a unit. We're applying it to a general view. Okay, let's just keep going. Okay, so before we talk about how the z-score is being affected, understand how regular data is being shifted. So if we add something or add or subtract something to all of our data sets, okay, so all of our numbers, then what that's going to do is it's going to increase your center, your percentiles, min, max. It's going to increase or decrease by that same amount. Okay, but the measures of spread, like the interquartile range, your regular range, that stuff is not going to change. Okay. Now, if we multiplied or divided by a constant, your measures of position, so center, percentiles, and so forth, that's all going to be multiplied or divided by that same constant. And your measures of spread are also going to be multiplied by that same constant. So I think it's best shown through this box plot. So here you can see that range is increased by that constant, okay, along with every single value. Okay, so our z-scores. When we figure out the z-score of every value, okay, that's finding the distance from the mean. Okay, when we find that, we can plot that new data set for each value. Okay, it's not going to change the shape of my distribution, so I can still see the same shape should still be there, and the center is now going to be 0, and that the standard deviation is going to be 1. Okay, let's see. You compare this to a normal model, okay? Normal model would be like your, perfect world, right? The middle average is 50%, perfect is 100%, worst is 0%. That's, where everybody falls around 50% mostly, right? Because that's average. When we compare it to a normal model, the normal model we use Greek letters, all right, mu and theta. We use these because they're not numerical summaries. Remember, they don't have units, okay? That's why we're using the Greek letters, okay? They're based on a model. Let me show you, let's do a graph. I do better with visuals. Okay, so let's say here we have, don't read the question yet. So first, let me explain this. This is now our new mean. Okay, we've changed our data set. The average is now 0. And now we measure everything a certain distance. And we want to be 1 standard deviation away most of the time. All right, so we talk about 1 standard deviation, 2 standard deviations, 3 standard deviations to the right. Or you can go to the left. 1, 2, 3. Now I can be 1.4 standard deviations away. Don't know why I did the extra decimal. I can be 4.2 standard deviations away. I can be 0.19 negative 0.19 standard deviations away. I can be anywhere down this number line, okay? But right? It's easier to talk about it when, as units, so 1, 2, and 3. So we want things to fall into a nice little bell curve. Maybe you've heard that before. I know I say it all the time. All right, so this is what you want data to do, okay? Everybody to be right around the middle, okay? Now, if we say they're within 1 standard deviation, that means either a positive one or a negative one. That's where we typically have most people, and that's what we have. 68% of the people are going to be within 1 standard deviation of your mean. Okay, so 1 standard deviation above the mean would be 34%. 34% are 1 standard deviation below the mean. All right, if we go out to 2 standard deviations, now we've included more people. So now we're at 95%. And we go out to 3 standard deviations, and now we're at 99.7. Okay, so most of our data should be within 3 standard deviations. Okay, I say most because we have a 0.3% chance it might fall outside. All right, think of your outliers. Okay, it happens, but not often. Okay, so for this example, all right, here we have in the Winter Olympics, total time of 120.86 seconds for 2 runs, about 1 standard deviation slower than the mean. Okay, so they're here, and this is again our mean. So if a normal model is useful in describing slalom times, I don't know what this is. Okay, about how many of the 48 skiers finishing the event would you expect skied slower than him? So let's see. We want to know who skied slower. All right, well, if this is average, right, here we start getting below average. So here is where they are. Well, we want to find out how many people are here. Okay, well, we know 68%, so that means 32% should be these 2 outsides. So that means this piece and this piece should be 16% and 16%. 16 plus 68 plus 16 should get us 100%. So 16% should be less than our 1 standard deviation. So 16% of the people, and it said, let's see, 48 skiers. So we do 16% of 48 skiers. Okay, we do that on our calculator. We get about 7.7. So let's just say safe. We say 7 skiers did worse. Okay, so that would be a normal model. Okay, you're comparing them to everybody else, but not knowing everybody's like specific data value. You know, it's your distance from the mean. Okay, let's do another one. A big one that you guys typically will see is the SAT, PSAT, any standardized testing. Okay, so here we have an overall mean of about 500 and a standard deviation of 100 for all test takers. Okay, so suppose you earned a 600 on one part of your SAT. So I am big on pictures. So here, let's just draw our normal model. So here is where our mean is going to be, and we have a mean of 500, and we typically do 1, 2, 3, 1, 2, 3. I did not do a very good job with that. Okay, what I mean by that is your 3 should really be where it hits, okay, because there should be barely any data outside of 3 standard deviations. Okay, so I'm going to space these out a little bit more. Okay, so then we have a standard deviation of 100. So 1 standard deviation above would be 600. Another 1 standard deviation, 700. 3 standard deviations, 800. We go 100 lower, and this is where we're at. Okay, so suppose I earned a 600 on one part of my SAT. So where do I stand among everybody else? Well, that is 1 standard deviation above the mean. So I did better than all of these people. Okay, well, I know that from here to here, 1 standard deviation is 68%. So, and I also know that from the middle to the end should be 50%. And this part is cutting that 68% in half, so that's 34. So 50% and that 34% get me 84%. So I would be told I'm in the 84th percentile, 84th, I don't know why I didn't add the TH, 84th percentile. So that means I did better than 84% of the other participants. Okay? That's what that means. Okay, worst case scenario. So what would happen if we were 5 standard deviations above the mean? Okay, so think about that. 5 standard deviations away, I mean, that's, you're 0.3% in that little bit, right? So it's really, really far. So what does that mean when I get that? What's the likelihood of that? Okay. A Russian mathematician kind of played around with this theorem about what are the chances of us having a data set that far with that kind of standard deviation. Okay, so let's do an example. Okay, so what does that mean? So if we were 1 standard deviation away, okay, but that's not really an extreme case, is it? 1 standard deviation away, I mean, we did that in the last thing. We were 84th percentile, okay? That's not that extreme, so we're not really going to use this, okay? That's not extreme value, right? Russian guy said he was doing really weird distributions, okay? So if we think about for 2, okay? So for 2, we do 75%. Oh, well, I guess I should do the actual formula for you. Yeah, it was 1 minus 1 over k squared. So for this one, we do 1 minus 1 over 2 squared. So that's 1 minus a fourth. So 0.75. That's where we got 75% of the values must be within 2 standard deviations. Okay. Well, that makes sense because we should actually technically have 95, right? So, okay, again, not the best case scenario, right? We want to go more extreme. So let's try a little bit further. Let's do 3. So we plug that in. Change my color. So we do 1 minus 1 over 3 squared. So we get 1 minus, well, 1/9. Okay, what is that? 0.1 repeating. So we're going to have 88. So, silly pen. So 0.88. So 88% of our data must be within 3 standard deviations. Okay, well, yeah, we should actually have 99.7, but again, we're getting general ideas. So we keep going. So let's do it for actual extreme values. right? This is what would make more sense. So let's do 1 minus 1 over 5 squared. So that's 1 minus 1 over 25. So we get 0.96, which means 96% of our data should be within 5 standard deviations. So that means 4% of our data should fall on the outsides. Okay, so, 96%, that doesn't seem that far off, right? When you start thinking about things like that, right? But if I had something where it was 10 standard deviations, now we're getting a little extreme. Okay. Right. Hope that's making a little more sense. Okay, so what do we do if it doesn't fall within 1, 2, or 3 standard deviations, right? How do I find that percentile? Okay, there is a chart. You can look for your z-score. Okay, you can, let's see, it's in the table. You will have it on every exam, okay? So you just go to, let's see, if you find your z-score, remember you take your value, you subtract your mean, and divide by that standard deviation. So here, you get some decimals. So here they got 1.80. So you read the table as 1.8. So this is the 1's digit and the 10th digit. And then this side, you're going to look for the hundredths. So 1.80. Okay. So then here, that number is going to be 0.9641. Okay. All right, we can also use technology. Okay, so to find it on your calculator, you're going to want to go to second vars, so distribution. You go to normal CDF, that's the one that's going to be useful. So do normal CDF. I want here I want the shaded area. So notice that the left side is going on forever, so I'm just going to pick a really big negative number. So -1, and that's what that had earlier, E99. Alright, our upper bound is going to be 1.8. That's as high as we want to go. Our mean, our standard deviation, 0 and 1 in this case. So we paste it, enter, and notice what we get, 9641, which is exactly what the table gives us. So make friends with that, know it, that's what finds the area for your percentages. Okay? Alright, so let's see. This is just a snapshot from your textbook. So normal PDF, again, it's not as useful. You want to use the normal CDF. That finds the area under the shaded region. Okay? So let's do another example. So take a second to read this. So pause it. Okay, so in this one, I really think it just does it straightforward. It tells you that if you want to go the upper bound, okay, so you wanted to know here, so here's the mean, and you are 1.8 positive standard deviations from the mean, so you wanted to find this area. So you're going to go from 1.8 to about 99. Okay, that's pretty reasonable in this model. Okay. You don't need to go to forever. Okay, infinity. You don't need to go a billion. Okay. Yeah. Anyway, doesn't really matter. So let's keep going. So, what if we had to work backwards? So, suppose that a college wants your scores to be in the top 10%. How are we going to go about doing something like that? Again, I'm all about pictures. So, if we think about the normal curve, we want the upper 10%. Okay, so we want to figure out what that z-score is. All right, so we can go and look at our table, of course. So looking at our table, we find the percentage somewhere in there, and then we look at what the z-score represents. This one goes out to 1.2 and then 0.08, which is 1.28, of course. Of course, we can do it with our calculator, so we can go to second vars, so distribution, and now we can use the inverse norm. So, inverse norm. So what I want to put for the area in this case, now your calculator only works from the left-hand side, so it's always, okay, your calculator always does the left side area, or area of left side. So in this case, we're going to use 90%. So the area would be 0.9, our mean and standard deviation, paste, enter, 1.28, and even it gives us more exact than the table would. Okay? So handy dandy calculator, know and love those functions. Okay, so working with normal percentiles can be a little tricky. So I figured we'd do another problem. Okay, so we can work this one out together. Okay, so hopefully took a minute, paused it, read it. Okay, so what we want to do here is we've got, we want to fill our boxes to 16 ounces. Okay, if we did the normal curve, okay, whoa, that was a terrible bell curve. That was better, but whatever. Okay, so if we have our mean be here, if we set it right at 16 ounces, well then you're right, 50% would be underweight, and we don't want that. So he redid it and said the average is now 16.3 with a standard deviation of 0.2. Okay, so we can go up to 16.5, then 16.7, then 16.9 to 3 standard deviations. So, 16.1, 15.9, 15.7, and I am going to erase my bell curve and try that again, just because it's going to drive me crazy. Okay, I did it now. Had to pause it, I figured it out, feel better. Okay, a little off, but you get the idea with the numbers. So let's see. So now we want to know, all right, what fraction of the boxes will be underweight? Okay, so underweight means at 16. So not at 16.1, but I need to be, let's see, let me pick a color. Let's do red. I need to be right here at 16. So I want to know this area, because all of those are going to be underweight. So we get out our calculator. So let's see, second vars, normal CDF, lower bound, upper bound is 16. Our mean is now 16.3, and our standard deviation is 0.2. So here we get 0.067. Okay. So here we have that it would be 6.7%. Okay, So I would write it as, ooh, my pen is really acting up. So 6.7% of the boxes will have less than 16 ounces or will be underweight. Alright, we're almost done. Okay, so when can we use this normal model? Okay, histograms are good, but they're not as good, okay? Because look at these. Alright, the one on the left, this histogram, alright, I know some of you would see these and go, oh, well, those kind of look like outliers, so maybe this isn't very normal, okay? So we graph a normal probability plot, okay? So it's, okay, so you're plotting the standard deviations. So you're literally plotting, you're finding every standard deviation of every data set and you're plotting it. And when you do that, if it's normal, it's going to do, it's going to be linear. Okay, it's going to form a line. And while yes, there are some that kind of go away, much more of the data is linear. Okay, so you can see how that histogram could be misleading. All right, also with this one, okay, I can see kids have seen this and go, oh, well, that looks pretty normal. Okay, and they're like, that's like one off, right? That one had two. Okay, however, when we graph it, you can start to see that it looks more exponential. Okay, a normal probability plot has to be linear. Okay. So let's make a normal probability plot with a calculator. So let's go ahead and put these data sets into your list. So you want to pause that and do that. Okay, so you put in your data, and now we're going to turn our stat plot on. So second stat plot, turn this one on, and we're going to choose the normal probability plot, which is the last one. Don't get it confused with the dot plot. So we choose list 1, and here we can choose the axis to display on. If we choose Y, it's like the one I showed you before. Alright, and you can use any marker that you want. I don't know, let's try the crosses, right? Oh, I didn't change my window. I gotta wait. Silly me. My goodness, my calculator's slow. Okay, so zoom stat. There we go. Okay, and so now we can see what that looks like. Okay, I mean, it's not the best linear that I've seen, right? Especially that other one was a lot more linear than this. Okay, so again, just to make sure you understand how the graph looks, anything to, this is the y-axis, and anything to the left has a negative z-score, and anything to the right has a positive z-score. All right, and again, not that it matters in this case in making your decision, but it's just good to know how to read a graph. Okay? All right, well, I think that wraps up Chapter 5. Oh, besides the what can go wrong. Okay, so big issues, don't use a normal model when the distribution is not unimodal and symmetric. It's not going to do any good. It means nothing to you. Okay, if it doesn't appear normal, then it's useless to use the normal model as an indicator. Okay. Don't use the mean and standard deviation when outliers are present. Okay, you need to get rid of those outliers. Outliers are huge things that can greatly affect your mean and your standard deviation. So make sure you remove the outliers before you start doing your normal conditions or normal stuff. Of course, this always applies to everything, I think. Don't cut yourself short before you're done. Okay? So make sure you always use as many decimals until the end. And because there are so many different ways to get your information, okay, whether you use the table, whether you use the calculators, and even a difference between an 83 and an 84 can sometimes be a decimal off. So don't worry about the minor differences, okay? I'm not going to catch you off if you're a tenth of a decimal place off or something, okay? If you're like real close. You know, if you're obviously huge number differences are, I'm going to count those, but tiny decimal differences, not a big deal, okay? Because again, all our calculators do a little different, and especially if we use a table instead of a calculator, it can affect our answer, okay? All right, I'll see you guys next time in class for questions.